In the last couple of videos, we talked about ethane, where there is a carbon attached by a single bond, and then there's 3 hydrogens out here like this on each side. And I'm not going to depict the hydrogens for you anymore because you're supposed to understand that carbon always bonds to 4 things. So if you see only a sigma bond here, which by orbital you know is an sp3 and an sp3 overlapped into kind of a jelly bean shape here in the center between these 2 carbons, you should know that there's 3 hydrogens floating around out here, and by now you should know that it's a chiral center, meaning these can freely swivel and rotate. And then in lesson 5 we talked more about something called ethyne, which is a double bonded carbon. And by the way, when you get good at organic, you should start to pay attention to the fact that we don't list carbons anymore either. This double line tells you that there's a carbon here and a carbon here. And that's all you need to know, because from these carbons you should also know that there's 2 hydrogens, one here and one here, and one here and one here. You're supposed to know that from lessons 4 and 5, so make sure that you do. And moreover, you should remember that this is in a planar structure as a consequence, because the p orbitals that have these electrons out here and overlap to form this pi bond between them down here, they don't have any mass. There's nothing bonded to them. So on a microscope that could go down to the atomic level, you wouldn't see anything. Everything would be in these hydrogens and carbons here on this flat plane. You should know that. And the last thing you should come away with is understanding that since this carbon is only bonded to 1, 2, 3 other nuclei, that it's sp2 hybridized. Now in methane, it was bonded to 3 hydrogens and a single bonded carbon that's an sp3. And the easy way to remember that is that this always adds up to the number of bonds. 1 s and 3 p's is 4, 1 s and 2 p's is 3. Now let's talk about what happens when you form ethyne. Let's make ethyne. F means 2 carbons, so we know there's going to be 2 carbons there. And yne means triple bonded. Triple bonded. How does a triple bond form? Well, let's take a carbon. We'll take another carbon. And the easy way to do it is just write like this. Okay, there's 3 bonds between them. Problem solved. Well, carbon doesn't bond to only 3 things, right? So there's still going to be a hydrogen. And if you think about it, it's going to have to be shaped this way, because this nucleus is going to push as far away from these nuclei as possible. But all these electrons that are going to be hovering somewhere in the middle area are definitely going to repel these electron groups, so these hydrogens are going to be pushed straight out. This whole molecule has a shape like a hot dog as a consequence. It's not just 2-dimensional, it's like a line. And that's really interesting in terms of wanting to pack a fuel very tight, because aside from the polarity, you could stack another one like right here like this. Yeah, you could do that. And you could put another one over here like this. They can get really tight. You can really make some room in there for pressure. It allows these to bunch up. And that's exactly why we use it as a fuel, because although you might not know it yet, ethyne, yne meaning triple bond, right? That yne tells you the secret, not just the eth part, is also known in Carmen parlance as acetylene. Am I going to spell it right? I think it's acetylene. And the reason I don't like that is this ene in organic chemistry means double bonds, which is not correct. But this is the old name for it, and still today, when you buy it in a tank with the oxygen tank and set your torch up in your garage like my dad used to do with horseshoe nails, you see it's labeled as acetylene. But we're going to call it ethyne because that tells you the molecule you're working with. Okay, so what does ethyne with the triple bonds look like exactly? If you remember from the last video, we saw that when you have a carbon on a flat plane like this and you have these orbitals, p orbitals, that kind of overlap each other in this way. I'm trying to keep my C's kind of far apart, but it's messing with the diagram a little bit. These kind of merge into this nice little gradient structure, don't they? And it allows electrons to kind of form a bridge between these side-by-side p orbitals here. And that's really cool. Let's just draw it this way. Let's draw the bond like this. And they only form after this sigma bond exists, this jelly bean here. is very close to that jelly bean shape. Classic. Maybe that's how they came up with that candy, is someone was a chemist making fake flavors. Once you have this in place, of course the tightest packing you could have is these p orbitals. Imagine you're an electron somewhere in this orbital. Well, this is great for proximity to this carbon, but if you want to be close to this one, look how far you are. But if I put an electron right here, now I'm close to all 12 protons. That is exactly what they want to do, and that's exactly why these p orbitals are willing to overlap like this. These electrons are willing to be near each other and swirl around each other to give them the most equidistance from the most protons. If you add it up using some hypotenuses and square roots and stuff, you'll find that the most positive attraction is going to be right in this space over here for anyone outside of the original sigma bond. Now, with ethyne, we had hydrogen single bonded this way also, and that worked for us. But now we're going to add to this, because maybe we don't have enough hydrogens, or maybe we just want to triple bond things for fun. We could do that. If I want to triple bond this for fun, we're going to have to do it with another p orbital. And I think you're going to find, maybe I'll use a different color, that things tangential whenever possible are the way to go. So if I can go away from the page like this, I'm trying to kind of depict it here, and out of the page like this, and out of the page like this, and away from the page like this, you will create the same kind of pi bond, but at a 90-degree angle here. So you end up with, I think I actually got you a diagram that's nice and simple. Took me all of 5 seconds to produce it. So let's just bring the one out and I'll just zoom it up. Sorry for the blurriness, but this works for us. I want you to have a peek at these bonds here. This pi bond and this pi bond are at 90 degrees to each other. It's a terrible color to use, isn't it? Let's use the regular green. This is a 90-degree angle between the two. So is this. That gives them the maximum distance from each other. And this one here is going to be tangentially 90 degrees also. And that should make sense to us, right? And of course now my diagram looks like hot garbage. Well, let's come back to just the ethyne maybe. If I want to triple bond something, you think of this double bond here, there's still plenty of space out here in front of them. If I wanted to like come out of the page this way, that's totally exposed. And that's why these fill that space like that, and behind it like that. I'm trying to draw it kind of plainer there. When they form this, and it definitely does happen if you do your chemistry correctly, it's going to pull all of the bonds a little tighter, because these bonds all pull the two carbons closer together. If it's just sigma bonded, let's say the bond length is about 180 units, but when you pi bond it with these north and south here, it brings it down to, like, let's say 160 units, just a little bit tighter. And then when you bring in this third axis for a triple bond from these overlapping bulbs, it's going to get messy, so I'm going to take it away. You're going to shrink it down even more. And the hydrogen, as a consequence, isn't going to want to deal with all of these overlapping orbitals here. So it's going to always bond and push out this way. It will stay in a plane like this, because remember, these orbitals have no mass. There's no protons out here, so they only exist in an abstract fashion. They have no mass. They have no size. You can't see them with a magnifying glass no matter how large. They just have electrostatic negative power. Okay, so with ethyne, you get this triple bond, and it's made up of these two pi bonds, and it's made up of one sigma hydrogen bond. I wouldn't even call it that exactly. It's an sp hybridized orbital. We'll talk about that, because you have now this carbon only bonded to two things, another carbon and one hydrogen. So that's going to be an sp. Remember, these add up to the number of bonds there are. So if you want to think about it like diagrammatically, an sp is a lot closer to like spherical in shape. Maybe it looks kind of like this. And an sp2 is going to be a little more p orbital in shape, kind of like this. And an sp3 is a little more of a p orbital shape like that, and then a regular p orbital looks like this. You know? So just keep that in mind as we move forward, because we're going to actually start playing with reactions soon, and I want you to remember these orbitals are not the same shape, and it's dependent on how many other nuclei they're bonded to, not how many bonds there are in total. And anytime you have a triple bond, you're going to call this linear, because it's going to look like this. So now that you're an organic chemist, we're going to take that away, because you should know that these three lines by themselves create ethyne. This is the actual organic molecule diagram you should use for ethyne. You should know this means there's a carbon here and a carbon here, and you should know that carbon doesn't have 4 bonds yet, so there must be a hydrogen out this way. And that means you should know that this is a linear molecule. And if you want to get really smart, pull out your periodic table and tell me if it's polar or not. Yeah? Alright, I'll see you in the next video. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.